Our first lecture is going to be on velocity and motion diagrams. So when we look at this, one of the things that our whole goal in doing this process is that we want to describe motion. So to describe motion, with its basic parameters. And these basic parameters are displacement, time, velocity, and acceleration. I do not think, even though we'll be talking about acceleration in this chapter, we're really going to focus on it a lot more in the following, in chapter 2. But ultimately, okay, we have only one goal. We want to represent motion. And the way we represent motion here is that we draw accurate motion diagrams. And I showed you the process of physics. We look at some physical phenomena, and then we use physical principles to get some type of image. For motion, it's a motion diagram. And motion diagrams, then what they really do here is that they set up mathematical equations that allow us to calculate a particular number. So the way we're going to do this here is that to get to motion diagrams, we want to represent motion using what I call dot physics and arrows known as vectors. So that's where we're headed here. So you already are an expert at motion. The fact that you've been alive this long, you are. There's no doubt about it. So what we want to do here is that we want to put your intuition on motion into the language of physics. So I'm going to define speed, but I don't have to tell you what speed is. You clearly know what speed is. But let's start representing it in the language of physics. So by definition, we define speed as a measure of how fast something moves. Once again, like I actually had to tell you that. Of course you know that. But in the language of physics is we take this sentence and we draw it into an equation. Why do we write equations? It's because it's easier. It's a shorthand notation for an equation. So then when we write speed, it really means it's the distance over time, which really tells us is that how quickly does distance change with time? That's what this equation really tells us. And this is what we call a rate. And in a mathematical equation, we write this with the V, and that's because speed is an incomplete statement. It's embedded in the term velocity, and that's where the V comes from. And we then say that the displacement is the distance divided by the time. So this right here is our definition of speed. And once again, if I speak about this in the language of physics, what this says here is that speed is the rate of how fast distance changes with respect to time. So we could then go in and we could just do some simple examples. You know that 60 miles an hour is faster than 20 miles an hour. Okay? We know 60 miles an hour is faster than 20 miles an hour. But how do we write this so that it becomes a little bit more clear? Well, if I look at 20 miles an hour, and if I look at 60 miles an hour, we look at our definition of speed, and in each of these intervals, we are referencing relative to 1 hour. So it's the hour that's the same. What is different here is that 20 miles implies that I travel 20 miles in 1 hour, whereas in this case here, I am traveling 60 miles in 1 hour. So clearly, when I look at this equation right here, what I'm seeing here is that in each...
Are you going to take that?
Say that again? Was that a question?
No, sorry.
Okay. In each of these situations, we can see what I'm going to try to do is that I'm going to try to draw the time the exact same size, telling me that 1 hour is the same for both of them. But clearly in this case, this distance is smaller, and in this situation, the distance is larger. So the reason why 60 miles an hour is faster is because it covers more distance with respect to time. So then mathematically, the way we would draw this here is that we would then clearly say that 20 miles an hour is clearly a slower speed. This guy's clearly a faster speed. So symbolically, we want to draw this so that it shows this. So in this case, I'm going to say that this v is small. This v is large. So the question is, why is that the case? Because when I look at my times in each situation, they're exactly the same. So I'm going to have to move this down a little bit. They're exactly the same. The difference is that that distance is small, whereas in this case, that distance is large. That's how we define what we mean by speed in the language of physics here. So now if I keep moving along, I kind of said this already, but I should write this, and I should say here is that speed is an incomplete statement of motion. Because if you're trying to move your car to a particular place, speed is not a very good indicator of where you have to go. You know, you could just say, hey, where's your house at? Just drive 20 miles an hour. You already know that that's useless. What we have to do here is that we have to include direction. So what we find here is that velocity is the correct term to use to describe the state of the motion. And what we find here is that one uses vectors, which is an arrow, to describe velocity. And what we find here is that these have two characteristics. So what do I mean by that? Well, an arrow or a vector, what we know here is that it's an arrow. So if I look at this arrow, what I'm seeing here is that there's two pieces of information. One, we can clearly see that this guy right here is telling us about the direction. Which direction is the arrow going? And then there's a second piece of information, which is from here to here. And this right here, this represents the length of the arrow. And in mathematics, this is called a magnitude. So what we know here is that vectors have both magnitude and direction. So when we start to talk about vector quantities like velocity, if you only give me the magnitude, you could see that it's an incomplete statement. And look what I just said earlier here. Hey, where do you live? Just drive 20 miles an hour. You know that that's a useless piece of information. You need more information than that. That's why speed is an incomplete statement. So now what we want to do here is that we now define velocity then. Okay, so our definition of velocity goes like this. So the way we typically define velocity, because it is a vector, we start with the symbol v because it's v for velocity, and then we put an arrow on top of it. And that arrow signifies that it's a vector. So then if I look at this, it has two pieces. It has speed and it has direction. So what we know here is that the speed, as we've already described, tells us how fast something moves. And this is what we call the magnitude of the vector. On the other hand, the direction is just a direction. So what does the direction tells us? Well, it tells us which way. So this right here is our definition of velocity. It is a vector quantity. Only giving half of it gives you half credit. So how do I write a velocity vector? So the first thing that we want to do here is that we need to set up a coordinate system to tell us a direction. A lot of the times we will signify going to the right as positive and going to the left as negative. Another way that we can do this here is that we could set up a coordinate system where we then say going to the right means east, going to the left means west. So let's say I have a vector that's 20 miles an hour. So here I go. So let's say I have a vector. Let's see if I can be color coordinated. I use blue for 20. Okay. So let's say we already know that I had a blue vector earlier that was 20 miles an hour, and it was moving, let's say, east. Okay. So what does that mean? I come in and I draw my vector, And I'm going to say that it's 2 squares. So what I'm defining here is that my scale here is that from here to here, 1 square represents 10 miles an hour. So you can see here is that this square, this vector has 2 squares. So therefore, this automatically scales this, and it tells me the speed is 20 miles an hour. But then what I'm going to see here is that according to my coordinate system, this is in the direction of east. That's what that velocity vector tells me. On the other hand, I had a different velocity vector, and that was a larger velocity vector. Why? Because its magnitude was larger. But in this case, we're going to say that it's going to move west here. So how do I draw this? According to our coordinate system, it's got to point in this direction right here. But now I got to scale it. So I know that's 20, 40, 60. So then, due to the length of this guy, this immediately tells me that this here is 60 miles an hour. That tells me about the speed. But clearly this guy is pointing in the west direction. And that's what we have for velocity right there. So now let's keep moving along here. So what I want to do now is that I now want to analyze the motion of objects using velocity in motion diagrams. So I now want to move into motion diagrams because I said this was the most important piece of this chapter. This is how we represent motion. So let's look at that. Now remember, I'm posting these notes. Okay, so you know how you learn. So you do whatever you got to do that works for you. Sometimes you might be able to just listen and then look at what I post afterwards, or it might be better for you to write, but you got to pay attention to what's best for you. Okay, so here I go. So what is a motion diagram? Motion diagrams is a strobed image. And when we talk about a strobed image, what this really does is it gives us a history of the motion. So as an example here, I'm going to show you a young boy running to the right. We could call that the east. We could call that the positive direction. And I got this image right off the web. And it looks something like this. Okay, so here's my image right here. Now, there's a couple of things that we should really look at this thing here. Because when you look at this motion of this boy, you could see that it's clearly a strobed image, but it's a complicated motion. And maybe we should list these just to be nice and clear. So the first thing that you should pay attention is that each flash of the boy represents some time interval, right? So, for example, here we could come in and we can look at this boy right here and we could say, okay, this is my point 0, so that's 0 seconds. And if I look at this point right here, we could say that's, so from there to there, that takes a certain amount of time. So what we're going to do is that we're going to set that time interval as easiest as possible for us. So each flash of the boy represents, and I'm going to say it represents 1 second of time. It's more likely that, I don't know what the frame rate is this kid. It could be about a 15th of a second. In the old days, that's pretty much what the flash rate was. So that tells me is that every time there's a flash, the time interval of each image of the boy that you see, we're going to say is 1 second. Now, what you're seeing here is that when you look at the motion of the boy, it's complicated. Why is it complicated? Well, you see that his head does move up a little bit, but his arms and legs are really moving a lot. So what we want to do here is that we want to find a spot that stays relatively even here. And so what I'm going to shoot for, it's hard to tell, but I'm going to say that somewhere around his belly button, I'm going to say that that's relatively stable. By the way, it looks like his head is not moving very much, but there is a little bit of bobbing. So you could imagine here that if I pick all of these points here, and what I'm going to try to do here is that I'll do my best to get sort of like where, you know, he is moving up and down. Let's say that it does that. So if I look at this whole thing, you could see that this is 2, 3, 4, 5, 6, 7. So from when the boy initially enters the image all the way to 7, we would then say that that's 7 seconds. So that's what that strobe image is telling us. It's telling us the whole time here. Now, another thing that's worth looking at is that the strobe image also tells us about a horizontal distance. So the strobe image shows a horizontal distance. Now, what we want to look at is that how do we judge the horizontal distance? Everything has to be relative. So what I'm going to do here is that I'm going to come in and I'm going to draw vertical lines. Right? And as I draw vertical lines, one of the things that I want you to pay attention is that, note, I can't define a speed at 0. I can define a speed at 1, as you'll see here in a moment. But if I start to just draw these things, what we're seeing here, again, we said that the boy, that our best location was going to be the so-called center of mass. And one of the things that you may start to realize is that as this boy is running, you can see that these vertical lines are approximately constant. So that means if I compare this distance from here to here, and let's say I compare that distance from here to here, they look to be relatively constant. So what then this tells me here is that the spacings between these blue lines are roughly equal to a constant. So now we could sort of like summarize this thing. So if I summarize, what I see here is that the time and distant intervals are constant. And because they're constant, then that then tells me that the speed of this boy, no, we already know the direction because he's going right, but the speed of the boy then tells us that this speed and this velocity is constant. So therefore, this situation shows constant velocity. And the reason why it's constant is because its speed is constant and its direction is constant. So what we can conclude here is that we know that both of these are constant. So this immediately tells us here is that constant velocity, it means that the dots that we've drawn are equally spaced. And I won't write that down, but I will write it down as I start to look at the different situations of velocity here. So now, let's start to look at, start to analyze the motion diagrams here. So now what we want to do here is that we want to look at different situations of velocity and their motion diagram. So I just showed you what the first one was, and we'll say that, yeah, this is constant velocity. And because this is constant velocity, this immediately tells us that we have constant speed, constant direction. That's what we mean by this right here. So here we go. So what I'm going to do here is that I'm going to set all the directions to be in the east. So that means if I set my coordinate system and I call that my east direction, all my velocities are going to point in that direction. So I'm not going to add speed here. Excuse me, I'm not going to add direction. I'm just going to say they're all going east here. So now let's look at the details of how we define a lot of speed here. So let's, let's look at the details of speed. Okay, so this is really important here. Okay, because if you got to get this understanding in order to keep sort of like moving in the right direction. So here's what we know about speed. We already know that this is distance divided by time. It's that distance that becomes really important. So we know that constant speed has equally spaced dots. Okay, so we know constant velocity or constant speed has equally spaced dots. So let's focus on that here. So now, here we go. So this is my 0 point. And because this is my 0 point, you cannot define a velocity at 0. You need a displacement. So now I'm going to draw this as 1. I'm going to draw this as 2. I'm going to draw this as 3. And I can just keep going on and on if I'm thinking about the image of the boy. And we already said here is that this here is the east direction. So here I go. How do I define a velocity or a speed? I need this interval right here. Okay, I need that interval. That interval tells me that it's the separation between dot 1 and 0. Only then can I come in here and draw my velocity 1. So in other words, my velocity 1 at point 1 is equal to the displacement before 1. Well, all of my time intervals are going to be fixed here. Now let's look at interval 2. So if I look at my speed at 2, I have to look at the interval before 2. And this is speed 2. So then speed 2 here depends on the interval 2, 1. And then if I look at the speed 3 here, it depends on that interval right there. So then if I look at 3, you could see here, it depends on the interval prior to 3 here. So you could see that I can keep following this process here. But this is what you want to pay attention to. And you'll see that this will pay huge dividends if you pay attention to these intervals here. So now we can define what we mean by a slower and a faster constant velocity. So here I go. So if I have a slower constant velocity versus, let's say, a faster constant velocity, what should I expect to see? Well, my dots have to be separated with equal spacing. So then if I look at my arrows should all be the same length. And in this case, you could see here that my velocity symbol is small. I drew it small because it covered a small distance in this time interval. That means that I have a constant velocity that is slow. On the other hand, I could have dots that are farther apart. So when I go in and I draw my velocity vectors, you could see that they're larger, and therefore I draw a bigger symbol like that. So then in this situation, the reason why this is a large velocity is because it covers more distance per unit time. So this then would be the motion diagram for constant velocity. Right? This is the motion diagram for constant velocity. Okay, so now if I start to look at this, now I can look at another situation of velocity and look at its motion diagram. So the second thing that we want to think about here is that we want to talk about changing velocity. And what we're going to find here is that there are two ways to change velocity. So the first way is that I can change speed while holding direction constant. Or I can have a constant speed but I can change direction. The fact that you define velocity as magnitude and direction, speed and direction, that means if you change any of those two, right? So I can say that if one changes either speed or direction, this changes velocity. And in the next chapter, when we say the word change in velocity, we mean acceleration. So we are talking about acceleration. I won't talk about the wording of acceleration because it gets tricky. And I think we need a little bit more experience with the motion diagrams before we jump into acceleration. So here we go. Let's look at these two situations here. So the first thing that I want to do is I want to focus on speeding up. Okay. So we know that in this situation, let me be careful here. So now we're going to talk about change. We're going to change speed with a constant direction. That's our first situation that we want to look at. And we know that if we change speed, we can change speed two different ways. We could either speed up or we could slow down. So let's talk about speeding up. So if I talk about speeding up, that clearly means that we are constantly increasing the speed. That really tells us, in the language of physics, is that the dots must get farther apart. That's what we mean by that. So let's look at that. So if I look at my arrows, let's start right here. And let's say that remember, I cannot draw an arrow at the first one at 0 here because I don't know the interval prior to that, but I can draw the interval, my speed right here. Why? Because I have an interval right here. This is my interval right there. That's my distance here. So when I look at my distance, I know that my dots all have equally spaced times here. So then I look at my speed 1 at that point, and it's that big. Now, if I speed up, the dots have to get farther apart. So then you can see here that this interval is clearly longer, telling me that I have a larger distance between the dots. So therefore, this has to give me a higher speed. And if I continue along the same way here, maybe I have a dot here at 3, and you can clearly see that in this interval right here, this distance is even larger, so therefore this vector has to be even longer, showing a higher speed. Look how I keep paying attention to the interval. Now let's look at the slowing down case. In the slowing down case, we know that we are constantly decreasing the speed. So now we know that the dots must get closer together. This makes it tricky on the motion diagram. Why does it make it tricky? So let's start to look at this guy here. Okay, so let's pick this dot right here. And we're going to say that this is 0. Again, we cannot do that. And so what I'm going to look at is that I'm going to look at this interval right here. So when I look at this interval, what you're seeing here is that this interval is a big interval. And because it's a big interval, that means I must have a high speed right here at that first point. Now, if I'm going to slow down, I have to have a smaller interval here. So one way of doing it is that if I try to put it in a straight line, it turns out that now I have things that are overlapping. And we don't want to have things overlapping. So for slowing down, what I'm going to do here is that I'm going to bring this down. And then what you're going to see here is that the first one, there's 1, 2, 3, 4. And the second set of dots, so if this is 1, this is also 1. Now this is 2 here. And you could see here that this distance here is smaller than from 0 to 1. So now what you're seeing here is that this distance is smaller. Therefore, this speed must be lower. But if I put them right on top of each other, then I have velocity vectors that are literally right on top of each other, which makes it a little bit harder to read. So then what do I do next? If I'm slowing down, I bring it down again. And then if that was 3 squares, now I'm going to set this to be 3 squares. And you can see here that now I have a smaller interval, and therefore my speed is even slower here at 0.3. So you could see how the arrows are changing in length here like this. But you gotta be able to sort of like draw this so that it's clearly showing you this. So you can see here is that this is the motion diagram. Right? This is the motion diagram for speeding up while going in a constant direction, right? While going in a constant direction. And then this guy right here is going to be the motion diagram for slowing down. So now we could look at sort of like examples. Here's one example that I'd like to share with you. Again, I got this off the web. All I did was type strobe image. And this is of a diver coming down. And so what I did here in this situation is that I went ahead and I automatically just drew the dots to just save time. And what you're seeing here is that you could see I tried to put the dots where the center of his white trunks. And what you're seeing here is that if you look at the dot separation, you could see that that distance is small, but every split second, the separation between the dots is getting larger and larger. So the fact that the dots are separating clearly shows that the diver is speeding up while going down. We all say that, of course, something moves faster as it falls, but guess what? You know, maybe I should have maybe labeled this as 1, 2, 3, 4, 5. This is proof. A strobe image is proof that that is the case. So from here, what I'm going to do here is that now I'm going to go to the second case. And then we want to start to look at examples. So our second situation, what we're going to be doing here is that we're going to be looking at constant speed. Oops. While changing direction. And this is what we call turning. Turning is a form of changing velocity. So what we want to do here is that we want to set up a situation that looks something like this. So assume you are driving towards the fishhook at the end of Highway 1. So if you're careful and you look at what the speed limit says here, the speed limit on the fishhook is 20 miles an hour. So that's the maximum speed. Let's assume that you decide to drive the maximum speed, which is 20 miles an hour. We immediately know that that speed implies that we have equally spaced dots. Now, of course, if you drive faster, I really don't want to, I don't really want to care. I don't need to see that. I don't need to know that. So now, here's what I'm looking at here. So if I'm looking at this, what you have to do here, so to stay on the fishhook, one has to constantly change direction. By constantly changing your steering wheel. Right? You have to constantly change the direction of your steering wheel in order to stay. So we could imagine then that we do something like this here. I know that if I look at the fish hook, I'm going to imagine that I come into the fish hook and I'm coming in at constant speed. And then once I'm in it, I then start to change my direction. But my dots have to stay equally spaced. So if I'm looking at my arrows are all fixed, but you're seeing here that they're looking something like this here. So what I'm saying here is that my velocity is changing, but my speed is fixed because the spacing of the dots are all the same. And as a consequence, that's what we mean by a motion diagram where we have constant speed and change direction. Now, as an example of what we have here, here's something that we can do here. I could come in here and I have this image here that I want to share with you. And this is an example of a motion diagram with this type of characteristics. And what you're seeing here is that we have a baseball bat with a red and blue flasher. So one of the things that I want you to pay attention to is that you could see that the red flasher is closer to the handle of the bat. The blue flasher is closer to the end of the bat. So what you want to pay attention to here is that in this situation, this is the back swing. And then the other one, this here is the forward swing. Now, what you want to realize is that in the forward swing, look at the dots. See how the dots are closer and they're getting farther and farther and farther apart? That tells you that not only are you changing directions, but you're speeding up. But at this point right here, look what you actually see right here. What you're seeing here is that these are equally spaced dots. Therefore, it must be moving at a constant speed, but at the same time, constantly changing directions. So this shows constant speed, but you can clearly see the dots are changing directions. So therefore, I have changing directions. And I could say the same thing over here. Look at this. You can see these dots are equally spaced. But this one clearly has a higher velocity, and this one has a lower velocity. But that's an example of that type of motion diagram.